It is a great honor for me to welcome Professor Nakanishi from Nagoya University, Japan. And I believe, is this your first time in India?
Yes.
Then very warm welcome to India as well. And so he's going to continue our discussion on cluster algebras. And he's going to be here for a week and give 4 talks. And so his first talk is cluster algebras.
This is a talk of everything, for four talks.
Okay, 4 talks. This is the first of 4 talks. And it is
dilogarithm.
Cluster algebras and dilogarithm identities.
That's right. Thank you very much for organizer for inviting me. And my title of the talk is not yet announced, so I wrote it. The title is Cluster Algebras and Dilogarithm Identity. The plan of my talk is in the first 2 lectures I explain about basics of cluster algebra, which I want to need in the later section. And then in the later section, in the lectures, I talk about its application to dilogarithm identity. Yes. And more specifically, the title of my talk today is a cluster pattern. First lecture, actually. So this is the first part of cluster patterns. And actually, I don't talk about cluster algebra itself. But I rather want to underline cluster patterns. And often people talk about cluster algebra structure. They don't mean algebra itself, but actually appearance of this cluster pattern or structure or in a various field. So that is my concern. And the main reference for the first, today's talk is Fomin and Zelevinsky's Cluster Algebra 4 paper, which is very, very nice papers, and will explain the main result of these papers. And first, I want to start, really start from the scratch and explain the semi-field, which is very, very important algebraic structure to define cluster pattern. Yeah. And definition. So P, semi-field, P, I use this notation throughout following this Fomin and Zelevinsky paper, is a defined as, first of all, it is a multiplicative abelian, multiplicative group. Yeah. So it means it defines multiplication is defined. And this group unit element exists, and the operation or inverse for multiplication exists. And abelian means it is commutative. Yeah. And in addition to this structure, it has a so-called addition. Which is written as in this symbol, and it is a pre-binary operation. It is possible commutative. Itself and associative. And distributive in a usual sense with multiplication, namely if we have something like A times B plus C, then you can expand it. Yeah. So first main known example of semi-field is field itself. So field field, any field, is not a semi-field. It's a little bit contradictable or statement, but because a field include 0, which does not have inverse, so with multiplication, so this is not a abelian multiplicative group at all. So I give several examples, which I'm going to use in my lectures. So first natural example is you can consider a subset of a rational field of rational function. I mean, a positive one. Yeah. Then you do 0, and this is closed under the multiplication, and also you can add, and that's it. Oh, and so one of the important points is no subtraction is defined at all. Yeah. So that is one main point, because 0 is not, including 0 is not compatible with this structure. And so as the set of real or positive, real positive numbers are a semi-field by usual. So by usual multiplication and addition. Yeah. The second example is called universal semi-field, which is very useful. So it's different from the Fomin-Zelevinsky's notation, but I use this kind of symbol where U is a multi-variable, formal multi-variable, say of n, so n, so they are formal multi-variable. And so QU is a usual rational function field. Rational function field of U, which is not semi-field, as I mentioned. But you can consider a subset of this. Say the member which I forgot to mention. Say, suppose if F such that Fu has a positive rational expression. And I explain what this means. For example, if you have a function of two variables, U1, U2, sorry, U1 square minus U1. This has a minus sign, which is not good, but you can write it as this way. And this is a rational function with a positive form. So this is a positive rational expression. And so this function, if you write this, is a bad form. But if you write this in this way, you can see that this is a member of this. So a little bit non-trivial notion. And you can see that this becomes a semi-field, by ordinary multiplication and ordinary addition, yeah, by multiplication and addition in a rational function field. Because in this form, you can multiply it, still you have positive expression, you add it, you still have a positive expression. But if you make a subtraction, now it makes a problem, yeah? Okay. And third example, or maybe start to write here, is called the tropical semi-field. with the same type of multi-formal variable. So one of the main function of a cluster algebra is it is quite a good friend with tropical calculation. And so this is the first appearance of tropicality in my lecture. And this is, I like this trop U, and as a set, we define it is a just a Laurent monomial, yeah, with a constant term, 1. Yeah, so it is it's something like that. We have any variable, but we also include negative powers. So it's a Laurent monomial, yeah, with a constant term. Yeah, and you multiply. By ordinary way, it becomes a abelian multiplicative group. Yeah? Multiply with them, it's just addition of them here. But so by usual multiplication. Here, if you define this, then that's not good because then we have 2 terms. So we need some special operation, which is called tropical sum. And the definition is if you have such 2 terms, say, and we have another one. Then I define our new Laurent monomial with its power being minimum of AI, BI. It's a good exercise to check that it is obviously commutative and associative, but it's a good exercise to check this distribution property, and then it becomes semi-fit. Yeah? And you can replace this to max, but it's a kind of matter of convention. If you want, you can do it. Yeah? In my case, this mean is more convenient. And there is a natural semi-field homomorphism called tropical semi-field homomorphism. Which from universal to tropical one. It is just described by the following one, then otherwise, then semi-field homomorphism automatically determines everything. And I give you some example to get a feeling of this map. So suppose you have such rational function with a positive expression. Then what will be its image? It's just homomorphism. So we just calculate each image, and this means it's just taking the common lower power of this one, and this one U1. It is actually U1 zeroth power. So U1 is 0. So it's just a this power, and here the common lowest power is here. Yeah. So somehow you take reading term, but the reading term it's not really common, but somehow lower part of U. So it's a kind of generalization of the reading term, and they are. So very broad specific, it's a reading term of this positive rational function. So So the tropical, we sometimes called this a tropicalization map, or is just taking the reading term, very bold operation, but somehow this is very good property, which is compatible with cluster algebra structure. And one other things which is useful is a trivial semifield. Say there's no notation, but I like this. So it should be a abelian multiplicative group, so it should include one. So this is a trivial abelian multiplicative group. Then 1 plus 1 is, of course, there's no other choice but setting like this. Yeah, and you should be also careful because you may want to calculate 1 plus 1 is 2. It's wrong with this multiplication, yeah? And that's it. So this ends the example of semifield, and also now introduce a related concept which I'm going to use. So P, take any semifield which you choose. Then this itself is a multiplicative abelian group. And then you can just simply define, so this has an operation, multiplication and plus. Yeah. Then you can associate its grouping. Yeah. Because it is an abelian group, yeah, you can consider. And by definition, this group ring multiplication is common with this one. But this is a member of this one is a formal sum of elements of this one, and this formal sum is given by different plus. So it is kind of external addition from point of view of this one. It's very different things. In this group ring, you can't use this. You only allowed to this operation. If you just see as a subset of this, and then you can make addition, yeah? That kind of thing. So you have to distinguish these things. And then you can further define, since this, one more remark, this group ring turned out to be a domain, which becomes a domain, which means there is no zero divisor, domain. This coming from the fact this is a semifield. And then you can define by usual method a fraction by taking the quotient of this, you can define fraction field. It's a field, yeah? Fraction field of ZP. Yeah. So this is just ordinary field where you just use this operation, and of course you have a division, but it's a part of multiplication. Okay, so this is something which we are gonna use in a cluster pattern setting. This ends the first section. Is there any concern about these points? Who asking? Tropical map, yes? It doesn't matter. Yeah, it doesn't matter. It is well defined. Yes. Yeah. Now I'm talking about a cluster pattern, or I forgot. Yeah, before that, seed and mutation. Yeah. And my talk is a kind of extension of the definitions of Jacobs in the last talk, because he is talk about this situation of this tropical semifield. It's also called without coefficients. And this P is actually sub as a is a kind of field for coefficient. So and it is called a seed with coefficients, and that's what I'm going to discuss. So first of all, to define something about cluster algebra, you have to fix natural number, which I mean the positive integers. Yeah, and also so it is eventually called rank of what I'm going to define, say seed, or rank of cluster pattern, or associated cluster algebra. You have to first fix it, and also together with n, you also fix one semi-field, yeah, and which is called the semi-field, or coefficient field, coefficient semi-field, coefficient field of same things, yeah. And then I also fix so-called what is called ambient field, which have been already appeared, or this things ambient field. Here I mean we consider a field which is first of all QP. I recall you that once you have a semi-field, you can have an associated fraction field of group link of P, which is called QP. And this is just a field, so you can use it a coefficient, and you can define a function or field of W. And W, once again, is some formal variable. And I'm going to define a cluster variable as a member of this field. But you don't have to care about what is the choice of these things. It does not actually appear at all in the following talks. So anyway, having this setting, you can define, first of all, the concept of the seed, yeah, which is the extension of the Jacobs one, so seed. Seed is a triplet of three things, which I'm going to explain. So B, it is a matrix, so I wrote its component as Bij, and its size is n. So n by n a matrix, so it is a skew symmetrizable matrix, integer matrix. N by n, integer matrix. And here, skew-symmetrizable means this is a definition, that there is some diagonal matrix. There is a diagonal matrix. D, whose it looks like this, whose components are positive integers. And such that once you multiply from the left, say, so this becomes a skew-symmetric. This becomes skew-symmetric. Means that if you take a transposition, then it becomes A minus B, T, D. The transpose is the same, so I can write this in this way. Oh, something is wrong, no? I'm confused. No. It becomes, sorry, dBT is skew-symmetric. Yeah. And so this D is called our skew-symmetrizer. factorizer of B. And this B itself is called exchange matrix of seed. For a simplest situation, this D can be, B itself is already skew-symmetric. Then one can replace it with quiver, which was explained by Jacob's talk. So, but this is a more general situation. And next, we introduce X, which is an tuple of elements in our ambient field. So I forgot to introduce the notation F for this ambient field. So it is a rational function of some formal variable with coefficients in QP, yeah? Such that x1 to xn, by some technical assumption, are algebraic independent. Algebraically independent. And this x is called cluster variable. And in my talk, I simply call this x variable because it's simpler. And one other thing, it's about y. It's another tuple of elements, and this element itself live in coefficient field P, which you choose at the very beginning. And so there's no any relation, any other condition. So you can choose any kind of any tuple, and it is called coefficients. And for simplicity, I call it y variable. There is a little bit unfortunate story that so this notation is due to Fomin and Zelevinsky, and it's very popular one. But now there is another more also popular convention introduced by Fock and Goncharov, and unfortunately they call this A variable, cluster A variable. That is okay, but somehow this is called X variable. That's not good, yeah, because it certainly conflict with, and so. So this is due to Fock and Goncharov, but I don't use it. But somehow you have to translate every time when you have different notations. Yeah. Fortunately, they use this big character. It depends, but I don't know. Anyhow, that's one thing. And once you have a seed or notion of seed, you make a mutation. Yeah. And by the way, if you don't have any, so if you choose this as a trivial semifield, then the y is always choose 1, and you can somehow ignore it. So this is a situation where Jacob was talking. Okay. Next, I consider mutation. Now we make a mutation. So I don't freeze anything. So you can mutate every direction, and you introduce by mutating one seed, you get some other seed, which I call B prime, X prime, and Y prime, and the definition is as follows. So B prime, there is a formula, which I just write it down. You don't have to remember this at this moment, but if you want to study cross algebra, it's better to remember it, because that's basically what you only things you need to remember. And otherwise, you have something. There is some structure for this formula, but I don't explain this. So if I, j, not the same. Where this symbol I use everywhere, if say it is a number or real, say integer, this is called the positive part of the number. So it's a maximum of 0 to a. Or more simply speaking way, it is positive or including 0 then. But if it is negative, it is 0. Yeah? So you somehow cut off the negative part. And this is a so-called piecewise linear operation where the tropicalization get into the business in cluster algebra. Anyway, just this definition. And for a simpler case, when you consider this skew-symmetric integer matrix, and you write it a quiver, then this is exactly the same as quiver mutation, which Jacob already explained it. Anyhow, this is a mutation B. Next, I like the mutation of our x variable, which is, it becomes simple when I is not k, it just remains the same. And here, when I is k, it is negated, and we have some unusual formula for some people, but which turned out to be very useful. So just write the formula. Yeah? And using this notation, so minus b, j, k, plus, and this is some multiplication of some monomial, and then we have this is element in P, and we have some element in ambient field, which I'm going to write. It happened, these complicated things happen when I is a k, I is k. And so I have already explained this notation, and one thing I have to explain is this notation, which also quite common in cluster algebra business. It is called y hat variable. It is just defined by yk times the following combination. B is this matrix, right hand side, yeah, the left hand side, and we just say product like this. And this is an element, yeah, in ambient field, F. Yeah. And so this operation is in ambient field, and this is just a multiplication of element P, which is considered as a part of QP. And so they are still belong to these things. And one thing we have to check is this algebraic independent condition is preserved. But you can easily prove this from this simple transformation, which I leave it as an exercise. And one more thing. Well, so please don't be overwhelmed by this ugly formula. It's actually very good formula. And there is for every part has a good meaning, but I will maybe have a chance to explain it later. Okay, so y hat variable is a kind of a dual variable, and so in x variable is complicated here, but y variable is complicated to the other side. So this side is simply a takes the inverse of, and that's it. Yeah, and actually it corresponds to this part. Yeah, and other part is happen when I is k, and it is a little bit ugly. So you have to make some multiplication. When you make a mutation to index I, then you make a multiplication of something related to this yk variable. So the variable looks like bki plus and 1 plus yk minus bki. So this is a formula. Which one you may talking? I forgot this one. Here? Above. Ah, this one. Yeah, thank you very much. Yes, when I use this bracket, I always mean this one, but sometimes I forgot to wrote. I forgot to write. Yeah. Anyhow, so this operation is P. So this is the element of P, multiplication of them. So it gives some transformation of n tuple of y variable, and that's it. And the business of cluster algebra is to show that this set of transformation is a very good one. Yeah. And there are many things which fall into this transformation. Okay, so but I may have to mention a factor which I implicitly use, which was again mentioned already, but sorry, something. Mutation, if you make twice, once again you make the mutation to using the same formula for everything is primed, then it becomes it comes back to the original one. So it is involution, and also to say that this is seed, then you have to first claim that this matrix is a skew-symmetrizable matrix, right? But this is actually guaranteed by the following a simple observation. So if D is a skew-symmetrizer, of B, then D is also a skew-symmetrizer of B prime. So by the same skew-symmetrizer, they become skew-symmetric. It's very convenient. So they share the common skew-symmetrizer. And also I mentioned that this is algebraically independent variable in our whole ambient field. So this is certainly a seed. Yeah? So it defines a new seed. Okay. And in many situations, you have a simplified version of a seed. First of all, by looking at these complicated things, first you notice that mutation of B matrix is very important because this data is used whenever you make a new mutation. Yeah. So in fact, that's why it is called exchange matrix. So it is kind of a DNA of the mutation. Yeah. And it determines this formula completely. Yeah? So next observation is Y itself is defined by, so this doesn't include any X variable, of course. On the other hand, this X variable mutation, Y variable also involved to here and here. So you can define Y variable mutation independently with respect to X variable, but you can't do in the opposite way. So from this, you first of all derive a little bit simpler notion of what is called Y seed. So you just ignore X variable. Still, it makes sense, yeah. And you just only consider this variable and. This mutation appear in the first course, first lecture of today, and in the Trunka's lecture, he said this is a mutation of cluster X variable. Yeah. Also, when you take P to be trivial, semi-field, then a Y variable becomes trivial, and you really, it's just identity 1 is 1, and so you can forget about it. And furthermore, everything, 1 plus 1 is 1, you can forget it, and here you forget it. So now you have a seed without Y at all. So this is the one which was Jacob explained, and from this general point of view, this is called our seed without coefficient. Seed without coefficients. And from this point of view, this seed is called a seed with coefficients in P. Yeah? Because y variable is considered as a coefficient by some reason. And well, one more remark is you can actually plug in these things and somehow multiply these things. You somehow see some more familiar formula of mutation. Inverse here, and multiplication, this one is for the first term, and multiplication, this is a second term, and this y variable appear as a coefficient. And this is maybe more common expression, but this one is actually much better expression from the point of view of the structure of this transformation. So since I want to tell these things, I wrote this expression. Okay, so I have, how many minutes? Okay, so next I'm going to the main object of my lecture. It is called cluster pattern, but it's already implicitly defined by Jacobs, but without this name, yeah, cluster pattern. Section 3. So it's just a seed arrangement with mutation. So I explain it. So once again, to discuss with cluster pattern, which is my main object, you first fix the rank and the coefficient semifield. Yeah, and then we introduce the following notion. It is called Tn is called n regular tree. It's just a tree graph with such that any vertex has n edges. So it's better to write it explicitly. So it always becomes an infinite diagram. I mean, n regular tree just by means the following one. So n equal 2 case, and we put a label with edge label with edges, such that edges are labeled, by 1 to n, so such a way that 1, 2, 1, 2, 1, 2. So from each edge there are two edge from each vertex there are two edges such that they are labeled by 1, 2. Then we have the following things, and then equals 3 case stay. You can always write just this most universal or tree graph you write. Yeah. So this is a Tn. Then exchange cluster pattern is assignment to each vertex the seed of which I introduced, namely cluster pattern. With a pattern with coefficients P is a, let's write this as a sigma. It's assignment of sigma seed, which I explained, to each vertices. By the way, I use notation. So Tn itself is a graph, so it consists of two parts, vertex and set of edges. But often we write Tn itself also means the set of vertices. Also, Tn denotes the set of vertices. Which is convenient. Then for each vertices, you attach a seed where sigma is a seed. So, okay, I put, I'm sorry, I changed to the superscript, everything, bx, txt, yt, which is a seed with coefficients in P, which is just defined here, such that for each edge labeled in such a way, and suppose it is one is called T, and suppose T prime, then such that for each situation, then we have the mutation of sigma T is sigma T prime. And so it means for each vertices of tree graph, you attach a seed such a way that these two seeds are connected by the mutation. Because of the involution property, this one-sided definition is well defined. Yeah. Okay. So this is called a seed pattern, and you can similarly you can define Y seed pattern, cluster Y pattern, or cluster pattern without coefficients. Yeah. Efficiency. Yeah. So it's for each set you have something like this for each vertex, or you have something like this. Yeah. And cluster algebra itself is just algebra is a sub-algebra in your ambient field, which is generated by xt belonging to one particular cluster pattern. But since I don't use this algebraic structure at all in my talk, I stop discussing this cluster algebra, but I rather concentrate on deal with cluster pattern. Yeah. So this is more kind of more base. It's an underlying notion of cluster algebra, but it's kind of more basic and important. Okay. Now, so main purpose of cluster algebra theory is to understand the property of a cluster pattern. Yeah. So namely the seed related by mutation. Yeah. So and today I explain you the one of the most fundamental result on this cluster pattern, which is called the separation formula. And from my point of view, this formula is a reason why cluster algebra is important, or cluster pattern is important, other than this famous Laurent phenomenon. Yeah. So to discuss with this, now I introduce the so-called initial point on your tree graph, yeah? So when you have a tree graph at your, by your preference, you can choose any one point as a special point. And it is called initial point. Then, so fix T0 as the initial point. Then, suppose you have a cluster pattern. With general coefficients. And then, first of all, you have here a seed, a special seed, which corresponds to this initial point. It is called initial seed. And you have some general point, T. And the main purpose of cluster algebra problem, main problem is express the variable at arbitrary point in terms of by your initial variable. Yeah? So it's called initial variable. And the problem is in a good way. Yeah. You really don't. So basically, everything is just determined by the initial seed. So everything is, in principle, written as a function of initial seed, but writing as an explicit expression is something what we don't expect, but somehow more kind of a good expression which can be used in a several purpose. And that is a separation. One answer is a separation formula which has been obtained by Fomin and Zelevinsky, and that's I'm going to explain. And to this purpose, I introduce three things. I name them, they are named as C matrices, G matrices, and F polynomials. So I introduce them. First of all, do it in order. So it is an assignment of integer square matrices for each vertex such that it satisfies the following recursion relation. It's completely determined by the following initial condition. Yeah? First of all, as an initial condition, so everything is actually depend on your choice of T0. So first of all, it starts from identity matrix. Yeah, I is identity matrix. Anybody. And then it's kind of mutation for this matrix, mutation, direction. So if you, now you understand this notation. So suppose you have an edge, you attach CT and CT prime, then the CT prime, its component is determined by some formula. Once again, you don't have to remember this, but I need to write it. Otherwise, I can't explain anything. So I just write. So when J is K, then we have a negation, and otherwise, so it's very similar to B matrix formula, and in fact, it is introduced by such way. But anyway, Okay, so this is a formula, such formula. It's quite similar to the parallel structure to B matrix formula. And I'm going to explain the real meaning of this formula in the next lecture. So first, today, I just define those things. And I'm going to soon finish my talk today. So Z, it's also arrangement, assignment of integer square matrix, GT. Once again, it is given by initial condition G at T0 is identity matrix. Then we have a mutation formula, which is defined for these things, which I somehow skipped to write, and it's things this is simpler when J is not K. And minus Gij. And L is a summation indices to N and GLT. B, L, K, T plus. And one more term, minus. Yeah, we have minus sign here, which is not contradiction at all. L is 1 to N. B. Okay, C, T. Oops, IL. Plus. And you may ask a question if T is, you forgot to write T, but it's not a misprint. So not a misprint. Not B-I-R-T. Only here, oh, by the way, I have to introduce the convenient notation where I should have written when, oh, sorry, this one is T, and so this is the first time this appear, and I have to write somewhere, which is good. So I write sigma T0 is a sigma is a BT0 XT0 YT0 is simply omitting these things because those are initial, special. So this is an initial, but also this one is an initial one. But others are not. Well, I will explain everything maybe in my next two lectures. So next lecture, so you just I just write our definition. It's clear that by this you can define a set of matrices associated to each vertices. And finally, one more thing is called F polynomials. It's an assignment of, once again, a set of polynomials at each vertices T, which I'm going to write. So FIT, FT is actually consists of NT such that each FIT is actually a function y which live in say So a little bit abusing of the notation, but this is a universal semi-field associated with a formal variable y, and it is a function of phi with a positive rational expression. Yeah. And once again, this is defined by initial things which starting from a trivial rational function. Then we have a mutation formula. Well, if you missed these things, don't worry, it is written in a form in Zelevinsky 4 paper, so you just look at there. But in my talk, I need to define it. So when I is not k, it simply it doesn't change at all, but otherwise it is defined by some rational or positive rational expression of the former one, such a way. It's complicated, I admit, but I have to write C, J, K, T, plus it's some multiplication of y variable times f of J, T with B, J, K, T plus. And the formula continues, it's rather, and we put minus sign for both. Times f minus b, j, k, t plus, and it closes. Okay. So this is this happened when I is k. Some formula, yeah? Some rational transformation. Yeah. So I am going to write and the theorem for those things which I introduce. First of all, this name should be justified. Namely, apparently, this is just given by this positive expressions, and you can repeat. You always have some positive expression with respect to this variable y, but the theorem is that, and it is called Laurent phenomenon. In this context, this is the result by Fomin Zelevinsky Cluster Algebra 1, that every such rational function with positive expression fyy is indeed a polynomial. In y. Yeah. This is one way to state the famous Laurent phenomenon formula theorem for this seed with general coefficients, but it's reduced to this property. It's non-trivial things, and though it's not necessary to mention right now, but since it's convenient to say it, so positivity is also known. Positivity is actually of Jacob mentioned is due to a special case, Lee and Skiffler, and others mentioned. Everything is mentioned, but by Jacobs I omit, and so this is they did it for skew-symmetric case. And Gross-Hacking-Keel-Kontsevitch, Hacking-Keel-Kontsevitch, which proved for general way by some other methods that there's every this the same polynomial, now polynomial, every fit. Y is a polynomial with positive coefficients. is a polynomial with positive coefficients. With positive coefficient, yeah. By the way, proof by Lee and Chiffler is considered as an elementary one. Though it's very complicated, it takes 40 pages of paper, and they actually don't prove everything, but they somehow consider some special cases, and they didn't explicitly expose the full proof, but nevertheless, it is an elementary one. But and then they say that it can be extended to symmetrizable case as well, but do it is very technically concerned. But still, but if you wish, you can do it as your project to extend the result. On the other hand, Gross-Hacking-Keel-Kontsevitch proof is a constructive proof, so they kind of construct the solution of this system by some Lee algebraic and toric geometric method. Anyhow, that's a kind of a side remark from my things. And main theorem today, I'm going to finish now, is a separation formula. Fomin Zelevinsky, Cluster Algebra for people. And the statement is as follows: everything, yeah, those xit, yt, is expressed by these datas and also bt using these c, c, and f things. So it's kind of a factorization formula, I would say. So xi of it are expressed by initial variable xj without anything. It is initial variable. Then its power. First of all, we have G matrix here. So this is a G matrix part. Maybe I emphasize that here G matrix appear, yeah, as a kind of a leading term. It's not reading, but and as a part. We use f polynomial. And f polynomial itself is just a rational function, but you somehow evaluate at any semi-field by replacing this positive expression by your replace t with p in p, then you have element in p. Yeah. So, and also you have sorry. So this is fit, and you here you plug in your initial y hat variable, which I introduced at the beginning when I defined the mutation. So this is initial y hat variable, and this is calculated in your ambient field. So this one is initial y hat variable. In the next lecture, I record this once again, so you don't have to worry. Yeah, I just see this result today. Yeah? First encounter. So now y variable is represented by initial y variable only, and here we have C matrix appear. So it's a reading part over 1. Sorry, I omit many things. But and then we have a multiplication of your tropical, f polynomials here. Evaluated at p and multiply by bji t. Yes, so j is n. Let me check if I wrote everything correctly. Yeah. Yes, so everything is correct. And proof itself is just a easy one. So everything is determined by this mutation formula. So you just check these things satisfies the mutation of x variable and y variable. It's a very elementary calculation. You can do it, say, in a 10 minutes or so. Yeah. So by definition, this formula is. But finding this formula is a non-trivial part. And as I said, there are many situations where something which is not very known, but is recognized as having cluster algebra structure usually means that such things is mutate as x variable and y variable. And what is good about it? So just figuring out that it is identified with cluster pattern itself is not useful at all. It's just a recognition. But once you recognize it, you can apply this formula. That is a very useful thing. And tomorrow, I'm going to explain why this formula is useful. But just one word, this formula originally means a separation to this plus sign and plus sign in F. This was the original motivation of Fomin Zelevinsky. But different point of view, you can see this is a separation into two worlds. One is tropical world, actually, spot. And the other is non-tropical part here. And that point of view is important. So C matrix and G matrix carries the information of tropical calculation, which is much simpler than a rational function transformation. On the other hand, every non-trivial other part is encoded in this single polynomials. And I want to explain tomorrow that this non-tropical part is actually controlled by this tropical part. That is the beauty of cluster algebra. Okay, thank you very much.